Good afternoon, good evening, good morning, whatever time you are. My name is Sergio, and I'll be presenting my calculus coaster project, final project for elementary differential equations, uh, for the spring semester. Okay, so the Calculus Coaster Company has fortunately asked me to help build their roller coaster. And so this is the model that um, Bob, the architect, has made. And so we're going to solve for these constants and um, get this roller coaster built. Mm. All right, let's go. So some first things that we need to consider. Oh, actually, we'll go back. So how we're gonna do this is actually we're gonna find these constants at each for each junction using um continuity and differentiability. And what that means is for a function to be continuous, for at least a piecewise function, the y values for each of the sides has to be equal, and then for the differentiable part, the slope has to be equal on each part. So at this junction, this function has to be equal to this one, and then the derivative of this function has to be equal to this function at x equals 5, and then so on and so forth for x equals 20, x equals 55, x equals 85, x equals 109. All right, so just wanted to go over some basic derivative rules. Um, One of the key ones is the chain rule and the product rule, because if we go back, this, not this one, this one, n times quantity x minus 99 times cosine of pi over 4 quantity x minus 109 plus p. So that is going to be chain rule and product rule, because there's a function here, and there's a function here, and there's a function inside the cosine. So if we remember from our our problem stem, the model that the architect gave us has a bunch of constants. So actually, we are going to make them all into equations. So we have one, two, three, four, five, six equations, and we're going to set up equations for each junction. So one, two, three, four, five. And since we have to consider the continuity of each equation and the continuity of each junction and the differentiability of each junction, we're going to have 10 equations. So as I said before, it's going to be this function set equal to this function, and then for the continuity, and then the derivative of this function set equal to the derivative of this function, and so on and so forth for this junction, yes. And so um, I listed all these equations here. So continuity at x equals 5, differentiability at x equals 5. We will actually sub in for the value of x, and then we'll have variables to solve for. So let's take equation 2, for example. We're going to sub in x equals 5 here and then solve for a. So it'd be 9. So dividing both sides by 2 and x equals 5, we'll be able to solve for a. And then once we have a, we can plug it back into equation 1 and then solve for d. as long as we, sub in x equals 5, since that's where a junction is. And so on and so forth for equation 3, 4, 5, 6, 7, 8, 9, and 10. All right, here we go. And so basically, instead of doing all the algebra by hand, we can actually put everything into MATLAB and solve for the constants. So it's pretty cool. So basically, these are all the equations that I listed before. This is the function before junction 1. This is the function before junction 2, and so on and so forth. And then these are the derivatives of each of the prior equations. So df1 is the derivative of function 1, df2 derivative of function 2, and so on and so forth. And then, so here, we're going to set up the relationships of continuity and differentiability. So at junction 1, this is the continuity equation. So, and what we're doing, I guess, function call subs f1 x5 equals subs f2 x5. So is essentially this equation right here. And then the x5 portion of that function call is just evaluating the value x at 5. All right? Not too hard. Okay? And then obviously, as we said before, it's 10 equations. So for each condition at the junction. So this is the differentiability equation, and just go back to there. 2ax equals 972. That was just the derivative of this. So if you want to take the derivative of this with respect to x, you're going to bring down the 2 minus 1, that's the power rule, times a times x. So there you go. And this is a restriction boundary. I just screenshotted it from Desmos. So then we have 972x plus d if we're going to differentiate that. So the power of x is 1. So we're going to bring down, the 1 is implied here. And we're going to bring down the 1, and then 1 minus 1 is 0. So x to the 0 becomes 1. And then the derivative of the constant is just 0. So we have 972 here. Okay. And then and so on and so forth for these. Actually, we can quickly do these more complicated ones. So g sine of pi over 5 times x minus 55 plus h. So derivative sine is cosine. And this is a product rule. So the outer function is the sine, and the inner function is this pi over 5 times quantity x minus 55. So we're going to do derivative of the outside and then keep the inside times, so the inside is, as I said, and then times the derivative of the inside. So the derivative of this, so this is a constant. We can consider that after the derivative. So x minus 55, the derivative of x is 1, and then minus 55 is a constant, so 0. So that the quantity, the derivative of this x minus 55 is just 1. And then we keep the constant, so the derivative of the inner function is pi over 5. So remember, derivative of the outside, sine, is cosine. keep the inside, and then times the derivative of the inside, as we said before, pi over 5. Okay, so then we have x root x minus 84 plus m. Let's take the derivative of that. It's going to be, the k is a constant, so we keep it. And then x minus 84, the square root of this is, the square root can be written as a power to the 1/2. So we can bring down the power 1/2. And then, as we did before, minus 1 to the, take the power minus 1. 1/2 minus 1 is negative 1/2. The negative indicates it's in the denominator, and then the 1/2 is just the same square root. And then we have x minus 84. Okay. And then we can do this one too. We can do this one too. So now we have a product rule. We have x minus 99. This is a first function. And then there's a second function. And then there's an inner function here. Okay. So for the product rule, we can go here and see the product rule is derivative of the first function times the derivative of the second plus the first times the derivative of the second. Okay. So n is a constant, so we keep the constant. And then the derivative of this x minus 99 is just 1 as was before. So it's 1. That's the derivative of the first times the second, so you keep the second function. And then you're going to do plus the first function, so keep the constant n, x minus 99, times the derivative of the second function, so the sine, the derivative of cosine is negative sine, so you bring out the negative here. And then derivative of the inside of this function is pi over 4. So if you're taking the inner derivative, keep the constant, x minus 109 is 1, and then you multiply it by the derivative of the inside, and there we go. N cosine times pi over 4, n cosine of pi over 4 quantity x minus 109 minus n times quantity x minus 99 sine of pi over 4 times quantity x minus 109, and then multiply by pi over 4. Okay, there we go. So after that, the MATLAB actually does the derivative inside the code, so it's pretty cool. And all these relationships are as from the slide before. And then we can display each solution. Oh, we're going to solve for each solution, equation 1, equation 2. And what this does, it sets up a matrix and probably does some row reducing, and then they obtain each constant. It's pretty cool. So we can display each of the solutions like so. And then we get A equals 486 over 5. And actually, these are all just listed on the next page. Okay, here we go. So here are all the coefficients. It was pretty cool seeing this happen when I was doing the code. So yeah. And then, so apparently Bob made a mistake and he based off the y units. Oh my gosh, excuse me. by a factor of 91, so we just divided all the constants by 91. Yep, so here we go. Okay, so I just had to fix a mistake. So, um, yeah, the maximum height of the roller coaster is actually based off the cubic function here. And actually, I think we can see it in here. Yep, the maximum height is right there, following this cubic equation. So we can use that information uh, to find the maximum and minimum height. So what I did here was that if you remember, or if you learned in your calculus class, we can find the maximum and minimum of functions by uh, deriving and then setting equal to 0. And what that means is that the slope of the function or the derivative of the function equals 0. And so if we know that the slope is 0, that means that we have a line here. So whatever curve you have, it's going to go like this. And then the tangent or the slope is going to be 0. That means we're going to have a maximum if it's like this, or a minimum if it's like this. So either way, we can find that information um, using our derivative and setting equal to 0. And so basically, I have this quadratic equation because when you derive this cubic function, you'll actually get a quadratic, and you can set equal to 0 and find the solutions. If we have this function here, and if we plug in 25, uh, this should be over 91, and this should be over 91. If we plug in, call this G, plug in 25, we get 200, and then plug in 50, we get 14 point, and then this decimals. And so now we see that at x equals 25, we have the maximum. And then at x equals 50, we have the minimum for our cubic function. And then so we actually want to find the drop. So we're going to take, oh my gosh, there should be a negative there. We find the drop, it should be negative 185 and decimals because it's, down. Okay. I went to Google and then looked up world record um, wooden roller coasters. And so here we have a roller coaster. It's named Goliath, and the drop is 180 feet. And then El Toro 176 feet. And then this one is 162 feet. So comparing the drop to Bob's roller coaster, it's actually 185 point decimals feet. So actually on the order, it's 5 feet more than this one. So good job, Bob. You made a taller roller coaster. Um, I mean, uh, uh, guess a deeper, bigger drop for Bob's roller coaster. And then the tallest one is T Express 183 feet. Oh, excuse me. And then 181 and then 170 respectively. And the one that Bob designed, we calculated the maximum height is 200 and decimals feet. So Great job, Bob. Yeah, so our roller coaster pretty much topped each of these lists that I found on the internet. So that's pretty cool. So, um, actually, if we remember from the stem that this is the end of the roller coaster. So maybe, oh, function ends here. And you might be wondering, where is it gonna go? So Bob designed it so that the rider's gonna fly up and then they're gonna splash in some water. So we want to find out how long it takes for them to splash in the water. How fast were they going? How long does it take for them to reach the maximum height? And if the maximum height here is bigger than over here. So I will show you what I did for that. So we know that the initial height is 160 because we just plugged in 125 into that last equation. And then it was given in the stem that their initial vertical velocity is 48 meters per second. Oh, no, 48 feet per second. And then, so we can use the kinematic equation and plug in. We want to find out when they um, land on the ground. So set y final equal to 0. And then divide through by 16. And then we can factorize this minus t plus 5 times quantity t plus 2. And then we see that t equals 5, t equals negative 2. So we ignore t negative 2 because that is, we don't really consider going back in time. Um, but so yeah, t equals 5. That is the time it takes for the passengers to reach the ground. So count 1, 2, 3, 4, 5, and that's it's a fast time to reach the ground. So then we can use velocity equation, Vf equals V initial plus AT, and to find when the passengers reach the maximum height. Okay, so maximum height is if you're moving in a vertical direction, when you have reached the top is the turning point. That's when your vertical velocity equals 0. So we set equal to 0. The initial is 48 feet per second, and then acceleration is minus 32 feet per second squared. I should have mentioned that here. And then solve for t, you get 3.5 seconds for the passengers to reach the height of their trajectory. And then we can plug that back into our kinematic equation to find their final height. And then we find that out to be 196 feet in the air. Okay. So 3.5 seconds to hit the peak of their trajectory. 5 seconds for them to splash in the water. And then how fast were they going? Well, we'll see that over here. So we know our initial velocity. Well, we can actually take it from the top down because that will be easier for our computation. And then we see that the time from the top to hitting the ground is the same as the time for the ground minus the time they took to get to the top. So that was 7.5 seconds. So then we plug in for T and A and V initial. So V initial is 0. A is negative 32 feet per second squared. And then T is 7.5 seconds. So this becomes minus 112 feet per second. So it's pretty fast. This is their velocity when they hit the ground. So that's pretty fast. And so we did some dimensional analysis to find out how fast they're going in miles per hour. So minus 112 feet per second. There's 3,600 seconds in 1 hour. And then there's 5,280 feet in 1 mile. So those cancel and this one cancel. So we get 840 over 11 miles per hour. And this becomes, oh, excuse me, 76 .3636 miles per hour. That's pretty fast. That's really fast. That's like highway speed fast. That's how they're gonna hit the ground. And so um we notice that the max height the passengers reach is still less than the maximum height of the roller coaster. Remember, the roller coaster was 200 feet. Okay, here we go. So this is our curve for the graph. Yep. As you can see, it's all smooth, very nice. Then the passengers go, "Ah." Then they're climbing up. Then they go, "Poof." Oh my gosh. And you remember, it's just under, so then they probably made it like here. Yep. Well, that's it for my final project, the calculus coaster. I hope you enjoyed this video. And I had a lot of fun making this uh presentation, especially the MATLAB part. I was learning MATLAB, I guess, second time. So yeah, thank you very much and bye-bye.